good morning. Welcome to this video session. I remain Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session, we shall discuss oxidation numbers. This is a continuation of the video playlist. Is a video playlist on chemical reactions. So we've been discussing chemical reactions, and one type of chemical reaction is the redox reaction, reduction oxidation reaction. Some textbooks will say oxidation reduction reaction. So reduction oxidation reaction, redox reaction. Redox reaction is a type of chemical reaction, but before we go into redox reaction, I want us to discuss oxidation numbers, because oxidation numbers will help us to understand redox reactions as well as to balance redox reactions. Reduction oxidation reaction. Please, the entire information on chemical reaction can be found on you can go to my website, www.samuelchukwuemeka.com or www.chukwuemekasamuel.com, whichever one. You can also go to this website, chemical-reaction.appspot.com, chemical-reaction.appspot.com. So the notes, because we are going in this video, I will be explaining, and you can write if you want to, but it will be good if you pay attention. The notes, the definitions, the notes, the solved examples, the links to the videos, everything is contained in this website. So you can go to this website and you see the notes already. But if you want to jot down some things, that's fine. Okay, you can replay the video. So what are oxidation numbers? What are oxidation numbers? Oxidation number of an element is the number of electrons that the element gains or loses when in combination with another element or compound. So when an element reacts with another element or reacts with a compound, that element can donate or gain, and can donate or lose electrons. Okay, so we can say the element can donate or lose electrons. The element can also accept or gain, okay, or receive. This is or give. So when an element reacts with another element or with a compound, an element can react with another element, or an element can react with a compound to give another compound. Of course, when an element reacts with another element, it gives a compound. When an element reacts with a compound, it gives you another compound. So the element can donate or lose or give electrons, or the element can accept or gain or receive electrons. So, and this occurs, the atoms of the element are the ones that either donate or accept electrons. So, the number of electrons that an atom of an element, okay, that an element will, the number of electrons that an atom of an element would donate or accept when in combination with atoms of other elements or compounds is known as oxidation number or oxidation state. We also call it oxidation state. Oxidation states. So, and even, when you talk about when we do bonding, electrovalent bonding, covalent bonding, even when elements share, it's still either donating or accepting. So, like I said, oxidation number is the number of electrons that the oxidation number of an element is the number of electrons that the element gains or loses, donates or accepts or donates. Okay? Gains or loses, accepts or donates, receives or gives. How many electrons does the element gain, or how many electrons does the element lose when in combination with another element or compound? That is what we call oxidation number. Oxidation number can be positive. Okay, of course, when elements lose electrons, they are positive. Okay, positive ions, cathode ions. When elements gain electrons, they are negative. When elements, and sometimes the oxidation number can be positive, it can be 0, it can be negative. Okay, can it be a fraction? Later we can talk about that, whether it can be a fraction. But right now, let's focus on the oxidation number is an integer. It can be positive integers, it can be 0, it can be negative integers. Now we will later talk about whether we can have a fraction. Later in this video we shall talk about that. So that's the thing, that's the whole idea of oxidation numbers. We are going to give, now why are we studying oxidation numbers? Several uses. It has several uses. Number one, it will help us to balance redox reactions. Reduction oxidation reaction. Reduction oxidation reactions. Redox reactions is going to help us in balancing this reaction. And I'm going to take my time to explain this because looks like some people have issues balancing it. So I will take my time to explain it in not this video, but another video. So oxidation numbers will help us to balance these types of reactions. Oxidation numbers will help us in naming compounds. Naming compounds according to the IUPAC nomenclature. IUPAC nomenclature. Nomenclature means name. It means name. So IUPAC is a International Union of Pure and Applied Chemistry. It's an organization. International Union of Pure and Applied Chemistry. So in this video we shall be using the IUPAC nomenclature. I know some, when in Nigeria, for the secondary school level, they really expect you, it is expected, it's required that you name compounds according to the IUPAC nomenclature. Now, when you go to the university, you're studying medicine or nursing, you see professors using old names, the old or common names, the old names. Some people will say common names, the common names. I mean, it's different though, you know, like common name is used for, or market name, the common name of the market name. So this is a challenge using common names or market names, because sometimes there's a lot of compounds, there's a lot of chemical compounds. So sometimes it's a challenge unless you're a chemist, you're a chemistry major, you will work with compounds. But you know, when you have a lot of things to put in your head, you know, it's really something else, you know. So for this video, we shall be using this IUPAC nomenclature. I mean, I can talk about common names or the industrial name but we shall be using industrial names. These are you know, in the same. I mean, or you might, if you want to buy chemicals in the market, if you give them the IUPAC nomenclature, probably they don't know. They say, do you mean this? So it's good to know these industrial names, is good. However, for secondary school folks, it's required in Nigeria. Now, I don't know about some other schools, but it's required to know it. And we shall be using IUPAC nomenclature. In this video, oxidation numbers helps you to name compounds according to the IUPAC nomenclature, and among several other uses. Okay, so let's now discuss some rules, and then let's discuss some rules, because you need some rules for assigning oxidation numbers. Then we shall solve several problems. I have several questions here for us to solve. So, but before we do that, you can take down these rules. As I said earlier, it is here in this website. You go to this website, chemical-reaction.appspot.com. The notes are there. So before we solve problems on oxidation numbers, we have some rules for assigning oxidation numbers. Number one, the oxidation number of an element in the free state is 0. Yeah. I will be writing examples because I already have this in this website. Because I already have this on this website, I will not be. You can write. I will just be explaining and be solving examples, writing examples. But I wouldn't be writing the rules because I already have it here. So the first rule, the oxidation number of an element in the free state, when we say element in the free state, is 0. Any element, the oxidation number of any element in the free state, any element in the free state. Now, what do we mean by element in free state? When it is not combined with any other element. When it is not combined with any other element, the oxidation number of that element is 0. So the element could be monoatomic element, it could be monoatomic element, could be monoatomic aluminum. Aluminum is a monoatomic element. It could be diatomic. Diatomic hydrogen. Hydrogen is diatomic. Hydrogen is diatomic. Is a molecule. It exists as a molecule. Now, I said aluminum because I'm using American American pronunciation. Nigerians will say aluminium. So I said aluminum. Please, it means aluminium. Aluminium. Okay? It's aluminium. Aluminium. But Nigerians will say aluminium. Americans will say aluminum. So I mean it's the same thing. Okay. And sometimes the way they write it, Nigerians will say aluminium. Americans probably will write it this way. Aluminum. So I mean aluminum. Or aluminum. So it's a monoatomic element. The hydrogen is diatomic. It exists as hydrogen molecule, hydrogen gas. It doesn't exist as, the element does not exist as an atom. This element exists as an atom, monoatomic. Okay, one atom of aluminum. This is 2 atoms of hydrogen, or you can say 1 molecule of hydrogen. Hydrogen exists as a molecule, okay, as a gas molecule in the room temperature. Now, so diatomic hydrogen, the oxidation number of aluminum like this is 0. The oxidation number of hydrogen molecule, diatomic hydrogen, is 0. Triatomic, ozone, trioxygen, triatomic, ozone. The oxidation number of ozone is 0. Tetraatomic, phosphorus, P4. Now, before we continue, let me write there these prefixes. Mono or uni is 1. Monocotyledon, monoatomic. As you can see, I put monoatomic, di, tri, tetra. Monocotyledon, monoatomic. Monomial, a polynomial of 1 term, mono. Uni, 1. Unity, okay? But here we are using mono. Di or bi is 2. Dicotyledon, diatomic. With bi, you say binomial, a polynomial of 2 terms. Bilateral, bisect, cut into 2 equal parts. Bi or di, 2. Tri is 3. Triangle, 3 angles. Okay, a polygon of 3 sides and 3 angles. Triangle. Triatomic. Okay, 3 atoms. Trinity, 3 persons in 1 God. Trinity three persons in one God, Trinity, Holy Trinity, three persons in one God, God the Father, God the Son, and God the Holy Spirit. God the Father, God the Son, and God the Holy Spirit. Holy Trinity, three persons in one God. Tetra, or quad is four. Tetraatomic, tetrahedral in shape. The methane is methane, CH4. Methane is tetrahedral in shape. Tetrahedral in shape. Tetrahedral in shape. Methane. Tetrahedral in shape. Methane, CH4, the structural formula. Okay? Don't want to go to organic chemistry. But that's the structural formula, methane, tetrahedral in shape. Quadrilateral, four-sided polygon. Quadrilateral, have your square, rectangle, rhombus, kite, parallelogram, trapezoid, or trapezium. Right? Quadrilateral. Quadrangle, quadrant, your four quadrants. First quadrant, second quadrant, third quadrant, fourth quadrant. Tetraatomic, 4 atoms. Pentagon, 5. Hexagon, 6. Hepta, 7. Octa, 8. Octane. Alkanes, and alkynes. Nona, 9. Deca, 10. Decagon. Okay? We also have hendeca, 11, dodeca, 12. So this is, we're going to be using, because I put this here because it's important in naming in IUPAC nomenclature. It's important, the IUPAC nomenclature. So this is tetraatomic phosphorus, octaatomic sulfur, S8. 8. So any element in the free state is 0. That's number 1 rule you should know. Any element in the free state is 0. The oxidation number of any element in the free state is 0. Number 2, the oxidation number of any compound is 0. The oxidation number of any compound is 0. Whether it be binary compounds, binary compound is a compound binary, bi, as you can see here, bi is a compound made up of 2 elements, bi. So as you can, the thing is, most of these you really don't need to memorize. By the time you solve problems, it comes, you learn it. And sometimes you don't, once you know the prefixes, you can easily, IUPAC nomenclature is really nice because you can really name compounds easily. It's helpful to name compounds. Even in organic chemistry, it's very helpful to name organic compounds. I prefer it better than the industrial names, honestly. So, binary compound meaning a compound made up of 2 elements. For example, if we have copper chloride, copper is 2, chlorine is 1. Copper chloride. Okay? So you have copper 2 chloride. Now we you know, people will say just copper chloride, but we can say copper 2 chloride. Copper 2 chloride is a binary compound, so we put copper 2 chloride. So we use the Roman numerals. We use Roman numerals. We use Roman numerals. So 1 is this, 2 is like this. You please don't write it, you know, you have to write it well. 3 is this. You learned your Roman numerals in elementary school. Right? 3, 4, IV, 5 is B, 6 is BI, 7 is VII, the Roman numerals. 8 is VIII, right? Okay. 9 is IX, and 10 is X. Is that right? Is that right? Okay. So your Roman numerals is what we usually use on this. We're not gonna go for this one. We will not go beyond probably 8. I don't know, but we're going to just be solving now. So copper 2 chloride. Now, of course, this is the way we write compounds. As I'm going through this, I will be going back to what we've done before, what we've covered in other videos, so you can refresh your mind on it. So what does this mean here? The oxidation number of copper 2 chloride is 0. It is a compound. It is a binary compound because it is made up of 2 elements, copper and chlorine. Copper and chlorine. So the oxidation number of this copper chloride is 0. Now, when you now name this as copper 2 chloride, copper 2, this tells you that the oxidation number of copper alone is 2. The oxidation number of copper in this copper 2 chloride is +2. That is what it means. Oxidation number of copper in copper 2 chloride is +2. That's why we say copper 2 chloride, copper 2. And don't worry, you might ask me, how did you know we are going to get to all this? We will. Trust me, we'll get to this. But just know that the oxidation number of copper 2 chloride itself is 0. Oxidation number of copper 2 chloride is 0. Of any compound is 0. Now we can also have ternary compounds. I know some people will say, why don't you say trinary compounds? You know, that's a good question if you ask that. Ternary compounds. This is a compound that has 3 elements. A compound made up of 3 elements. A good example would be your potassium permanganate. Now, potassium permanganate is the common name. Potassium permanganate. That's the common name. Potassium permanganate. Manganate. However, I don't want us to be going with common names. Honestly, I don't. This is the common name, potassium permanganate. But I don't want us to be going with common names. I want us to go with the IUPAC name. Now, this is a ternary compound. It is made up of 3 elements. potassium, manganese, and oxygen. Okay? Potassium, manganese, and oxygen. So we look at this. If we are going to, the oxidation number of this potassium permanganate, okay, potassium tetraoxomanganate 7. Now, do not be scared at all, because some of you will be thrown off. How did he name this? That is why we are learning this topic, so you can know how to name it. Okay? But look at what I said here. I said potassium tetraoxo, 4 oxygen, tetraoxo, because tetra is 4. Then manganate 7. Now, don't worry, I will teach you how we got manganate 7. In a moment, I'll teach you how we got it. But just know that the oxidation number of potassium tetraoxomanganate 7 is 0. Just like it is now, is 0. Because it is a compound. Oxidation number of any compound is 0. Now the same thing goes with a compound that has 4 elements. Tetranary or quaternary compounds. Tetranary or quaternary compounds. Tetranary or quaternary compounds. A compound that is made up of 4 elements. The oxidation number of that compound is 0. The oxidation number of any compound is 0. Okay? So the oxidation number, an example of this is your sodium hydrogen trioxocarbonate form. Your sodium bicarbonate, that's the common name, is sodium bicarbonate. The market name is baking soda. This is your baking soda, that's the market name, baking soda. That's the market name. The common name is sodium bicarbonate. But the IUPAC name is sodium hydrogen trioxocarbonate 4. Now you see here, and don't worry, we shall get to it in a moment. This is made up of 4 elements: sodium, hydrogen, carbon, and oxygen. It is made up of 4 elements, that's why it's ternary compound. Okay. So, of course, your baking soda, you know what you use it for. It's a cleaning agent. It is also used for baking as a leavening agent, and also for cleaning as a cleaning agent, and so many other uses. So the oxidation number of this compound is 0. So that's the second rule. That's the second rule. Okay, third rule. Third rule is what we are now going to talk about. Please, I want you to listen well in this third rule. The third rule is that the oxidation number of each element, the sum of the oxidation numbers of each element in a compound gives you that 0. So the sum of the oxidation numbers of each element in a compound is 0. The sum of the oxidation numbers of each element in a compound is 0, because it's equal to the oxidation number of that compound. Okay, some textbooks will say the sum of the oxidation numbers of each element in a compound is equal to the oxidation number of that compound. Well, I said in rule 2 that the oxidation number of a compound is 0. So rule 3, the sum of the oxidation numbers of each element in a compound is equal to 0 because the oxidation number of a compound is 0. Okay? So let's look at this, for instance. Copper 2 chloride. If we want to find the oxidation number of chlorine, let us say we want to find the oxidation number of chlorine. So we can say here, let the oxidation number of chlorine be X. Oxidation number of chlorine be X. Let's call it X. So I'm still on this here. For this one, copper 2 chloride. Let's say you were asked to calculate the oxidation number of chlorine in copper 2 chloride. Okay. So for copper, we already know it's 2. We already know it is 2. So this will be for copper. Let me actually come here. Let me come here and write it. So we have copper 2 chloride. So for copper, we already know here that it is 2. For chlorine, let's call it X. Let's call it X. So this will be, now this for copper is 2 plus, because I say the sum of the oxidation numbers of each element in a compound is 0. So this is copper is 2 plus chlorine is X. X times 2. So 2 times X. 2 times X equal to 0. We want to find the oxidation number of chlorine. So this will be that 2 plus 2x is 0. So 2x is negative 2. And then x is negative 1. We divide both sides by 2. So this means that the oxidation number of chlorine in copper 2 chloride is negative 1. Remember, we said that oxidation numbers could be positive or 0 or negative. Okay. What if I know now? What if, because I said copper 2 chloride, then you will ask me, how do you know it is copper 2 chloride? I mean, from the formula here, you will see in many compounds. However, let's say you didn't know. Let's say you were asked to find the oxidation number of copper in copper 2 chloride. Okay, what's the oxidation number of copper? So if you were asked to find the oxidation number of copper, then you will now say, let the oxidation number of copper be X. In this case, be X. For chlorine, it is negative 1. And it is a rule. Don't worry, we will get to the rules. Like, I just want to take this gradually. Chlorine, we know is negative 1. Unless it is in combination with oxygen. Yeah. It's usually negative 1. Unless it is in combination with oxygen or fluorine. Otherwise, it's negative 1. It is one of the rules I'll give you. So, the oxidation number of chlorine is usually -1, unless it is combined with oxygen or fluorine. It is one of the rules I'll give you. So we now know that that of chlorine is -1. So, and then we know that the oxidation number of this copper chloride, copper 2 chloride, the compound is 0. So this will be X plus 2 times -1 equal to 0. X plus 2 times -1 equal to 0. So X minus 2 is 0, X is equal to 2. So that is why we call it copper 2 chloride. Copper 2 chloride. Okay? Does that make sense? Okay, let's continue. The next one, we are still on rule 3. I want to show you more about rule 3. I want to show you more. Let's do more examples on rule 3. Now look at the potassium permanganate. That is the common name. Okay. Another rule, like we want to find the oxidation number of manganese. Let's say we want to find the oxidation number of manganese. So let the oxidation number of manganese be X. Please, whatever I'm doing here, I took my time to write it well in this website. So here I want to, like, because I already wrote this already. So I already wrote it how you would solve it, showing all your work. So here I'm just doing the video, okay, rather than doing a lot of writing. So I'm going to write this KMnO4. Let me spread it out. So potassium, this potassium, we want to find the oxidation number of manganese in this compound. Now, we already know from rule 2 that the oxidation number of a compound is 0. We already know. So I'm using yellow chalk. Another rule is that the oxidation number, that's the next rule we'll talk about. Okay, rule 4. The oxidation number of alkali metals is always +1. For your level, just know this, it's +1. It's for your level. So this here is +1. The oxidation number of potassium is 1. Let me just put 1, okay? 1. We always want to put the sign. Okay, so in the final answer, I'll put the sign. Then manganese, let the oxidation number of manganese be X. And then another rule I'll give you is the oxidation number of oxygen is usually -2. Unless it is in peroxides. If it's in peroxides, it has a different oxidation number. It has an oxidation number of -1. Or if it is bonded with fluorine, we shall come to that. But this is not a peroxide. It's not. And peroxide has two oxygen atoms joined by a covalent bond. We shall come to that rule. But this is not a peroxide. This has 4 oxygen atoms. So the oxidation number of oxygen is usually -2, except in peroxides or if it is bonded with fluorine. So here it is, This is not a peroxide. This is not bonded with fluorine. So the oxidation number of oxygen here is -2. So, and we know that the oxidation number of the compound is 0. So we now sum it up so that we can find that of the manganese. So this is 1 plus x plus, this is 4. Don't forget this 4, 4 times -2 equal to 0. Because this is like saying K1, Mn1. But with 1 we don't write 1 as subscripts. No, we don't. So we just leave it like this. So this will be 1 plus x minus 8 equal to 0. So x minus 7 is 0, x is equal to 7. So the oxidation number of manganese in this compound is +7. I'm going to write +7, +7. We usually want to write +7. We do. But if you write 7, no problem. It is still correct. Okay? Now, how did I name this IUPAC nomenclature? So this is potassium, K is potassium, tetraoxo, tetra, 4 oxygen, tetraoxo, manganate, 7. You see that now? Potassium tetraoxomanganate 7. Do you see where the oxidation number is useful in naming the compound? Potassium tetraoxo, 4 oxygen, manganate 7. So this tells you already that the oxidation number of manganese in this compound is 7. Yeah, this 7 is from this 7. IUPAC nomenclature. Does that make sense? Now let us look at baking soda. Okay? So here in baking soda, we have, because I want us to find the oxidation number and then name it IUPAC nomenclature. You see how it's easier this way? Because you have so many chemicals. You have so many chemicals. Now, for this one, sodium hydrogen carbonate or sodium bicarbonate. Now, sodium hydrogen carbonate. Okay. We want to find the oxidation number of carbon. Find the oxidation number of carbon. Okay, sodium bicarbonate. That's the common name. Or baking soda, the market name, the industrial name. So, but let us find the oxidation number of carbon. And then we name this according to IUPAC nomenclature. The oxidation number of sodium is +1. I'm going to put 1 here. It's alkali metals. Alkali metals. The oxidation number of is the next rule we will talk about. The oxidation number for your level. Okay, for your level, the oxidation number of alkali metals is +1. Hydrogen. The oxidation number of hydrogen, that is another rule we shall discuss, but you can be writing it down, no problem. The oxidation number of hydrogen is usually +1, except in metallic hydrides. In metallic hydrides. Okay. Metallic hydride is when the hydrogen is combined with metal. Okay. Here, I know sodium is metal, but carbon is not a metal, or you can say carbon is a metalloid. Oxygen is not a metal, it's a non-metal. So, I mean, carbon, later we could go to periodic table. Carbon is, we can, here, just know that this is not a metallic hydride. It is not a metallic hydride, so the oxidation number of hydrogen here is +1. The oxidation number of hydrogen is usually +1, except in metallic hydrides. So this is not a metallic hydride, so this is +1. Oxidation number of carbon is what we want to find. I'm going to put this X. Oxidation number of oxygen is -2. -2. So, and we know that the oxidation number of the entire compound is 0. So now, we now have 1 plus X plus 3. Here, this is 3. 3 times -2 equal to 0. So 1 plus 1 is what? 2. 2 plus X minus 6 is 0. So X minus 4 is 0. X is equal to 4. Plus 4. X is equal to plus 4. So this means that the oxidation number of carbon in baking soda is +4. Let us now name this according to IUPAC nomenclature. So the name will be sodium, hydrogen, sodium, hydrogen, trioxo, sodium, hydrogen, trioxo, carbonate 4. Sodium, hydrogen, trioxocarbonate 4. That is the IUPAC name. Sodium, hydrogen, trioxocarbonate 4. 4 because of this 4. Okay? So please, let's continue with other rules. Rule 4. Rule number 4. The oxidation number of any alkali metal in any compound, the oxidation number of alkali metals in any compound is +1. Okay, for your level, I will say always +1, just for your level. Okay, the oxidation number of alkali metals in any compound is +1. That is for your level, just know it's +1. Now, what are alkali metals? The alkali metals are the group 1A. The group 1A element, group 1A element of your periodic table. They are the group 1A element of your periodic table. They are very electropositive, very, very electropositive metals. So you have lithium. Okay, you have the next now is sodium, natrium. You know, that's the Latin word, natrium. Okay, natrium. Sodium. Then you have potassium. So all these has oxidation number of +1. Oxidation number of +1. You have potassium. You have rubidium. You have rubidium, RB. You have a sodium. That is CS. And then you have francium. Fr. Alkali metals. So that is rule 4. Rule 4. So if you have, what is the oxidation number of sodium in sodium chloride? Your sodium chloride, that's your common salt. This is your table salt. Your table salt or your common salt. That's the market name, sodium chloride. So what is the oxidation number of sodium in sodium chloride? So this is a rule. We already know that sodium is an alkali metal. So we know that this must be +1 for sodium. So X, we can now put chlorine as X because we already know the oxidation number of sodium. The oxidation number of alkali metals in any compound is +1. For your level, just know it's +1. So this will now be 1 plus X is 0, X is -1. That is, so you now see the oxidation number of chlorine is -1. So I will give you all these rules so that whenever they ask you to find oxidation number of a particular element in any compound, just follow the rules that I give you and then you can easily get it, okay? Now, rule number 5. Rule number 5. The oxidation number of alkaline earth metals. The oxidation number of alkaline earth metals in any compound is always +2. The oxidation number of alkaline earth metals in any compound is always +2. Always +2. Always +2. Now, what are alkaline earth metals? Earth, right? When we were learning, when I was learning oral English, in Nigeria, so we didn't just do English. We were colonized by Britain, unfortunately. So we were colonized by Britain, unfortunately, and then we were forced to learn English. So when I was in school, if you speak your mother tongue, when I speak my mother tongue, like they write my name, this person didn't speak English. So at the end of the school, they spanked me for speaking my mother tongue. You know my mother tongue, right? You should know now. Come on. You should know. My mother tongue is Igbo language. So we learned English very, very well. Like we knew English writing, read a lot of novels, reading, writing. We even did oral English. I don't know if they are still testing oral English, but in the West African School Certificate, WAEC, West African Examination Council. So when we took English, you took essay, you take multiple choice, which includes comprehension. You take oral English, yeah, whereby you write the English word and you write the phonetic symbol, like you pronounce it, the phonetic symbol in the dictionary. Oh, wow. We even I had to take that, and I passed it. I thank God I passed it. So the TH, alkaline metals. So these are the group 2A. Group 2A elements. Group 2A elements in the periodic table. They are the alkaline earth metals. and the oxidation number of alkaline earth metals in any compound is +2. Always +2, always +2. So what are the alkaline earth metals? We have beryllium. We have beryllium, which is your Be. We have magnesium. Magnesium, which is your Mg. You have calcium. Calcium, which is your Ca. You have strontium, which is your Sr. You have barium, which is your Ba. And you have your radium, which is radioactive, radium, Ra. Okay, so these are your alkaline earth metals, which are your group 2A elements. Now, the oxidation number of these metals in any compound is always +2. So let's look at this here. Let's look at this compound here. You have calcium, you have this ion, tetraoxophosphate 5 ion. And usually you have calcium 2+, you have phosphate 3-. So this is 2, 3, and don't worry, by the time you do more problems, you will get all this. So this here, this goes here, and this radical goes here. This is a radical. So you have calcium phosphate. That is the common name. That's the common name. Okay, but we want IUPAC name. So this is what I want us to do here, folks. You're given this here. You're given this compound. And you're asked to find the oxidation number of phosphorus. Calculate the oxidation number of phosphorus in this compound. So we have this. I'm going to split it up. Calculate the oxidation number of phosphorus. So let the oxidation number of phosphorus be X. I use the yellow chalk. Calcium, we already know from this rule. We already know from this rule, rule number 5, that the oxidation number of calcium must always, must be +2, must always +2. So I put +2 here. Phosphorus, we don't know. I'm going to put X. I'm going to put X. And then here, O is -2. Oxygen is -2, except in peroxides. This is not a peroxide. Or if it is bonded with fluorine, it is not bonded with fluorine here. So it's -2. Now, if you think you would be confused here, you can always, you can split this up like this. If you think, because some people forget, this 2 is in parentheses. It belongs to phosphorus, it belongs to oxygen. So you can also write this like this. 3 P2O8. You can, especially if you think you will forget, whenever you're calculating. If you think you're going to forget, you might want to write it like this, if you want to. Okay? If you want to. But do not forget. Okay, I'm going to do it both ways, so you see. But I don't want to be splitting it, but you can split it. No problem. You can. But to make, in mathematics, we want to factor factorize. You want to factor. So you can write this plus 2, write this x, write this minus 2. Just, I'll do it both ways, but you can still do it like this. You can, especially if you're the kind of person that forgets this subscript. Okay, so let's do this. This is 3 times 2. I like getting from the subscript first. So this is 3 times 2 plus 2. This 2, don't forget it, 2 times x plus 2 times 4, 2 times this 4 times negative 2 equal to 0. Let me have space here. So 3 times 2 plus 2 times x plus 2 times 4, 2 times this 4, then times negative 2 equal to 0. See that? So this is 6 plus 2x. 2 times 4 is 8. 8 times negative 2 is negative 16. So negative 16 equal to 0. So this is 2x. 6 minus 16 is minus 10 equal to 0. 2x is 10, so x is 5. This implies that x is plus 5. Plus 5. If you want to do it this way, that's still fine. You're going to get the same thing. 3 times 2 plus 2 times x. Always do from the subscript, then multiply by the oxidation numbers. Plus 8 times negative 2 equal to 0. I have 6 plus 2x minus 16 equal to 0. 2x minus 10 is 0. 2x is 10. So x is plus 5. X is plus 5. So, this, we want to name this IUPAC nomenclature. IUPAC nomenclature. So this will give us what? It will be, with IUPAC nomenclature, it will be calcium, tetraoxo, calcium tetraoxo phosphate 5. Calcium tetraoxophosphate 5. Okay? Calcium tetraoxophosphate 5 for oxygen phosphate 5. And if you want to name this ion, because that's the next thing we will discuss this rule in a moment. This is tetraoxophosphate 5 ion. Tetraoxophosphate 5 ion. We'll come to that anyway. We'll come to that. So that is rule 5. Now rule 6. Rule 6. The oxidation number of fluorine is always -1. The oxidation number of fluorine is always -1. The oxidation number of fluorine is always -1. Now remember all these rules because it's important. The oxidation number of fluorine is always -1. We said the oxidation number of alkali metals is always +1. Oxidation number of alkaline earth metals is always +2. Oxidation number of fluorine is always -1. Always. So if we have something like bismuth fluoride, bismuth fluoride, okay? Bismuth fluoride, bismuth, fluorine, BIF3, because bismuth actually is 3 valency here, 1. This is actually is a halogen, 7 or -1. But we don't put the negative when we are doing the formula. So this is bismuth fluoride, bismuth fluoride. So if you want to find the oxidation number of bismuth in bismuth fluoride, actually bismuth fluoride is just a common name. We shall do it IUPAC name, but it's still, I mean, it's just a simple compound anyway. So we can say this to be X and fluorine is -1. So this will be that X plus 3 times -1 is 0. So X minus 3 is 0, X is 3. So you can say bismuth 3 fluoride. The IUPAC name, you can now have it as bismuth 3 fluoride, bismuth 3 fluoride. Okay? Or you can say bismuth fluoride, that's still okay. Rule number 7. Okay, we're getting there. The oxidation number of hydrogen. The oxidation number of hydrogen. Now this is oxidation number of fluorine in any compound, please. I don't know if I said of fluorine in any compound. Okay, because oxidation number of fluorine in its free state is 0. That's rule number 1. Okay, please. Oxidation number of alkali metals in its free state is 0. Oxidation number of alkaline earth metals in its free state is 0. Oxidation number of any element in its free state is 0. So what I mean by this is the oxidation number of fluorine in any compound is -1. Always -1. Always. So don't just think it's oxidation number of fluorine. No. If they ask you what is the oxidation number of fluorine, it is 0. Okay? But if they say what is the oxidation number of fluorine in any compound, is always -1. Number 7. The oxidation number of rule 7, the oxidation number of hydrogen in any compound is always +1. The oxidation number of hydrogen is in any compound is always +1, except in metallic hydrides. Except in metallic hydrides. So in metallic hydrides is -1. It is -1 in metallic hydrides. So what do I mean? Metallic hydride is when the hydrogen is combined with a metal. Okay. For example, nitrogen hydride. You have nitrogen hydride, you have nitrogen, nitrogen is 5 or -3, and hydrogen is 1. So nitrogen hydride is your ammonia. That's your nitrogen hydride. But of course, the chemical name is ammonia. Ammonia. What is the oxidation number of nitrogen in ammonia? What is the oxidation number of nitrogen in ammonia? So let the oxidation number of nitrogen be X. And then this nitrogen is not a metal. It is not a metal. So this hydride, because I know this is ammonia, but it is nitrogen hydride. It is. So the nitrogen is not a metal, and because of that, the oxidation number of hydrogen here will be +1. So what is the oxidation number of nitrogen in ammonia? So this is X, because this is like 1 subscript. So 1 times X. X plus 3 times 1 is 0. So X plus 3 is 0. X is -3. So the oxidation number of nitrogen in ammonia is -3. Because you know these rules help you so that you can find the oxidation number of any element when you know the other element in the compound, the other element or elements in the compound. So it helps. So in this case it's +1. But what if you have a lithium hydride? Lithium hydride, LiH. Lithium hydride. Lithium, of course, has valency 1. Hydrogen, valency 1. So lithium hydride, LiH. So here you can say you want to find the oxidation number of hydrogen here, because I want us to know why it's -1. Lithium we already know is +1 anyway. So hydrogen, if we say X, so this will be 1 plus X is 0, so X is -1. Now, you see now why in this, because hydrogen here is -1, here is +1, because the oxidation number of a compound has to be equal to 0. So sometimes your professor might ask you, why is it that the oxidation number of hydrogen in metallic hydrides is -1? It's a question they can ask you. While in other compounds is +1. Why? And your explanation will be, it is the oxidation number of hydrogen in metallic hydrides is -1, so that it can balance, so that the oxidation number of the entire compound is 0 to neutralize it. Because if this guy easily donates an electron, the hydrogen takes it. Okay? You know, metals are electron donors and non-metals are electron acceptors. So it has to be -1 so that the oxidation number of hydrogen in metallic hydrides has to be -1 so that the oxidation number of the entire compound could be 0. Will have to be 0. Okay, so note that. Alright? Does it make sense? So oxidation number of hydrogen in any compound is usually +1, except in metallic hydrides, where it is -1. Do you understand? Comprende? Una wataraya. Okay, the next one. Next rule is rule 8. Rule number 8. The oxidation number of oxygen. The oxidation number of oxygen in any compound is usually -2. The oxidation number of oxygen in any compound is usually -2, except in peroxides. Except in peroxides or when bonded with fluorine. Okay, or when bonded with fluorine. So let's look at these cases here. What is a peroxide? Let's start with peroxide. A peroxide is a compound that contains 2 oxygen atoms joined by a single bond. A peroxide is a compound that contains 2 oxygen atoms joined by a single bond. So the easiest example is your hydrogen peroxide, H2O2. It contains 2 oxygen atoms joined by a single bond. So this is your hydrogen peroxide. You also have another example is your potassium peroxide, K2O2. So with peroxides, let's find the oxidation number of oxygen in hydrogen peroxide. So we say let the oxidation number of oxygen be X. Okay, so let's go ahead and separate this, H2O2. So let the oxidation number of oxygen be X. And then with hydrogen, we just did hydrogen. We said that the oxidation number of hydrogen is usually +1, except in metallic hydrides, where it is -1. Oxygen is not a metal, it's a non-metal. So hydrogen peroxide is not even a metallic hydride, it's not. So the oxidation number of hydrogen here would be +1. So we now see, and of course the oxidation number of the entire compound is 0. So we see that 2 times 1 plus 2 times x should give us what? 0. So 2 plus 2x is 0. 2x is equal to -2. 0 minus 2 is -2. And then x will now be, divide both sides by 2, x is -1. So the oxidation number of oxygen in peroxides is -1. It's not -2, no. So in peroxides, the oxidation number of oxygen is -1. Now the other case is when oxygen is bonded with fluorine. Let us look at some examples. The first one, let's see oxygen difluoride. The common name is oxygen difluoride. That's the common name, difluoride. So let us find the oxidation number of oxygen in this compound. Let the oxidation number of oxygen be X. So let's separate it. So let it be X. I use my yellow chalk, put that. And of course, from what we did earlier today, one of the rules is that the oxidation number of fluorine in any compound is always -1. This is -1. The oxidation number of the entire compound is 0. So this will be X plus 2 times -1 equal to 0. So x minus 2 is 0, x is equal to +2. So in this case, we see here, we can now give the IUPAC name of this. So we can say that this is oxygen 2 fluoride. Oxygen 2 fluoride. Oxygen 2 fluoride. IUPAC name. Okay. And you know, if you're given this compound right away, oxygen 2 fluoride. Let's say you're given this compound and you're asked to write the chemical formula for this compound. So when you see oxygen 2 fluoride, you know it's oxygen and fluorine. Oxygen and fluorine. Already you know, okay, oxygen 2. So you have to put 2 right there right away. Oxygen 2 fluoride. You know it's oxygen 2. So you put 2 under oxygen. And of course fluorine is 1. It's 7 or -1, the valency. So it will easily accept 1 electron to achieve the stable octet configuration of noble gases. So you just, you do it this way, and this will be O1F2, which is OF2. Like, with that IUPAC name, you can easily know that this is oxygen 2 fluoride. Although, some people will argue with the common name oxygen difluoride, just put OF2. Okay, but this is I still prefer IUPAC name. Now let us look at another example. If we have this here, so as you can see, oxygen is the oxidation numbers of oxygen. When it is bonded with fluorine, it varies. For peroxides, it's -1. Then when it's bonded with fluorine, as we can see here, is +2. Another example, when it is bonded with fluorine, if we have O2F2, which is the common name is dioxygen difluoride. Dioxygen difluoride. That's the common name. So let us find the oxidation number of oxygen in this compound. So I'm just going to split it up. Let the oxidation number of oxygen be X. And then of fluorine, of course, is -1. So this is 2 times X plus 2 times -1 equal to 0. So 2X minus 2 is 0. 2X is equal to 2. X is equal to 1 plus 1. So here we can give the IUPAC name as oxygen 1 fluoride. Oxygen 1 fluoride. As IUPAC name. And this one is oxygen 2 fluoride. See that? So with oxygen 1 fluoride. Okay? Although you can say OF, because it's oxygen 1 here, 1 here, OF. Because this O2F2 still means OF, because 2 can cross out 2. Dioxygen difluoride. Okay? Or oxygen 1 fluoride. The IUPAC name. So as you can see here, the oxidation numbers of oxygen in compounds in oxygen fluorides, it varies. When it is bonded with fluorine, it varies. It's not a fixed one. But if it is in peroxides, it's -1. In all other compounds, it's -2. Okay? Let's do rule 9. Rule number 9. Rule 9. The oxidation numbers of chlorine, bromine, and iodine, is usually -1. The oxidation numbers of chlorine, bromine, iodine, these are halogens, okay? It's usually -1, except when bonded with, with oxygen or fluorine. Except when bonded with oxygen or fluorine. So we talked about common salt earlier on, right? Sodium chloride. We talked about common salt earlier on. If this is X, sodium is an alkali metal, so this is always +1. So this is 1 plus X equal to 0, so X is -1, chlorine. Okay? That's the oxidation number of chlorine in sodium chloride. Sodium chloride is a common salt. Sodium chloride. That's a table salt. Okay. The oxidation number of chlorine in sodium chloride is -1. Now, but when it is bonded with oxygen or fluorine, it varies. So, how do you know? Because you know, for instance, with fluorine, you know fluorine is always -1. So, with oxygen is -2, except with fluorine. So, you can find out the oxidation number of chlorine when it is bonded with oxygen or fluorine. You can. Okay, like I said, it varies. Let's look at an example. If we have dichloroheptoxide, the common name for this is dichlorine, not dichloro, dichlorine heptoxide, heptoxide, 7 oxygen atoms, heptoxide, 7, dichlorine heptoxide. So let's find the oxidation number of chlorine in this compound. I'm going to split it out. Let the oxidation number of chlorine be X. And let the oxidation number of oxygen. With oxygen is usually -2, except in peroxides. This is not a peroxide. That's number 1. It's not a peroxide. Number 2, it doesn't have 2 oxygen atoms. No, it has 7 oxygen atoms. Number 2, it is not bonded with fluorine. Okay, those are the cases we just talked about. So otherwise it's -2. So this will be -2. So, and of course the oxidation number of the entire compound is 0. So we have 2 times X plus 7 times -2 equal to 0. Right? So this will be 2x minus 14 is equal to 0. Right? So 2x is equal to 14. Hence, x is plus 7. X is plus 7. So the IUPAC name here, would be chlorine 7. Chlorine 7 oxide. Chlorine 7 oxide. The IUPAC name will be chlorine 7 oxide. Okay? Chlorine 7 oxide. Does that make sense? So please look at all these rules. All these rules. Because when we start solving problems, it will help a lot when we start solving problems. So it's better you know all these rules. Okay, rule number 10. Rule number 10. The oxidation number of a monoatomic ion. Let's get to ions now. The oxidation number of a monoatomic ion. What is a monoatomic ion? Mono. So this is an ion formed from one atom. Monoatomic. So this is an ion formed from one atom. You know, when atoms gain or lose electrons, they become ions. Okay? Charged atoms. An atom is electrically neutral because the number of protons is equal to the number of electrons. Okay, but when an atom gains an electron or loses an electron, it becomes an ion. Positively, when it loses an electron, it becomes a cathode ion, positively charged ion. A cathode ion. Okay, when we discuss electrolysis, you see why we call them cathode ions or cations. And when it gains electrons, accepts electrons, receives electrons, it becomes negatively charged. And that is anode ions or anions, short form anions. Positively charged ions, cathode ions or cations. Okay, so monoatomic ion is just an ion formed from one atom. The oxidation number of a monoatomic ion is just the charge on the ion. The charge on the ion. Aluminum will lose 3 electrons. Okay? This is an aluminum ion. So the oxidation number of this aluminum ion is plus 3. That's it. Plus 3. Selenide. Selenide is selenium ion. Selenium ion, which we call the selenide. Selenium ion, which we call the selenide. The selenide here, the oxidation number of the selenide is -2. So the oxidation number of a monoatomic ion is just the charge on the ion. That's all. Okay. This is a cathode ion, which is cation. And this is an anode ion, which is an anion, short form. Okay. Positively charged ion drift to the cathode, cations. Negatively charged ions drift to the anode, anions. We'll discuss that in electrolysis, okay? Now, rule number 11. Rule number 11. Rule number 11. The oxidation number of a polyatomic ion. Polyatomic ion. So poly means many. Okay, polygamy. Poly means many. Polymer, monomers and polymers. Okay, poly means many. If it is more than one, diatomic, triatomic, tetraatomic, and the rest of them. So the oxidation number of a polyatomic ion is the charge on that ion, of course. Now, but the oxidation number of each element in the ion, in the polyatomic ion, the sum of the oxidation numbers of the ions in the polyatomic ion, okay, because I don't want to say element, because when we say element, we assume in the free state. So I'm going to say this: the sum of the oxidation numbers of each ion in a polyatomic ion is equal to the charge on the ion. The sum of the oxidation numbers of each ion, okay, in a polyatomic ion is equal to the charge on that ion. So let's look at an example. If we have this here, chromium. So this is a polyatomic ion. Actually, it's a diatomic ion because it's an ion formed from two atoms, chromium and oxygen. So the old name for this is the dichromate ion. That is that's the common name. The common name for this is the dichromate ion. But let us look at the IUPAC name. First of all, let us find the oxidation number of chromium. Let us find the oxidation number of chromium in this ion. Let's do that first. Then we name this ion using IUPAC nomenclature. So we will say here, let me go ahead and spread this out. Just my style. Let the oxidation number of chromium be X. For oxygen, we know it's -2. -2. Okay, we know it's -2. Because number one, this is not a peroxide. Like oxygen is -2. It's not a peroxide, and it's not bonded with fluorine at all. So otherwise oxygen is just -2. So look at what I'm saying here. The oxidation number of each ion in this polyatomic ion, the sum of the oxidation numbers of each ion in this polyatomic ion is equal to this charge on the ion. So let's calculate this. This is 2 times X plus 7 times -2 equal to -2. So this is 2x minus 14 equal to -2. Okay, so 2x is equal to -2 plus 14. 2x is equal to 12. 14 minus 2 is 12. -2 plus 14 is 12. You owe 2, you have 14. That means you have 12. So x is equal to +6. +6. Okay? So if we have to name this, if we have to name it IUPAC nomenclature, this will give us heptaoxo, 2-oxygen, heptaoxo dichromate, 6 plus 6, heptaoxo dichromate 6 ion. Heptaoxo dichromate 6 ion. Make sure you put ion because this is an ion. Heptaoxo dichromate 6 ion. Okay? Alright. The last rule that we can start solving problems. We've been discussing a lot of rules. Well, as we discuss these rules, we solved problems. Yeah. So 6 plus 6 is the oxidation number of chromium in this ion, in the heptaoxo dichromate 6 ion. Now this 6 here is because of this 6. You see how the oxidation numbers are useful in naming compounds according to the IUPAC nomenclature. The last rule, rule number 12, last but not the least. So for all other compounds, for all other compounds we did not discuss in the previous rules, if you are given a compound and you're asked to find the oxidation number of an element in that compound, and you don't have, this wasn't what we discussed. Like if it's something that we didn't discuss, if it's not an alkali metal, if you don't have enough information, then you assume the oxidation number to be the valency. Okay, so this is what I mean here. I'm gonna bring a question so you can understand what I mean here. Let's say I have several questions here. I have so many of them. I have many questions here. So what I mean is this. Let's say you have let's say you're asked to find oxidation number of nitrogen in this compound, zinc nitrate. So look at what I'm saying about this rule. We are asked to find here oxidation number of nitrogen in zinc nitrate. Zinc nitrate is the common name, zinc nitrate. But you're asked to find it, and as usual, I want you to name it according to IUPAC nomenclature. So if you're given this, for instance, we didn't talk about zinc. We didn't. Zinc is not an alkali metal. Zinc is not an alkaline earth metal. So we don't know the oxidation number of zinc. But we are asked to find the oxidation number of nitrogen. Now we do know the oxidation number of oxygen is going to be -2 because this is not a peroxide and this is not bonded with fluorine. So the oxygen is -2. However, we don't know the zinc because we need to know that of zinc before we find that of nitrogen. So that's what I'm talking about. You have zinc, you have nitrogen, you have oxygen, 3, and then 2 here. So I separated it out. So here, for zinc, what would it be? And that is what I mean by rule 12. So rule 12 is when you are given a compound, okay, usually a compound that has 3 elements, at least 3 elements, that's a ternary compound of a tetranary, or quaternary, 4 elements compound. If you have an element in which didn't fall in any of these rules discussed earlier, then you assume, because for us to find the oxidation number of nitrogen, we need to know the oxidation number of zinc. We need to. However, we didn't mention zinc in any of these other rules, and zinc is not fluorine, it's not hydrogen, it's not an alkali metal, it is not an alkaline earth metal. So what will be the oxidation number of zinc? You now assume it to be the valency. Valency is the combining power of an element. The valency of an element is the combining power of an element. There are some differences between valency and oxidation number. However, in this case, whereby you have this scenario, assume that the oxidation number of zinc to be the valency of zinc. Okay? And the valency of zinc is, zinc should be 30, right? Zinc is 30. Yeah. Zinc is 30, right? The electronic configuration, we're talking of the valency based on the electronic configuration in shells. So zinc is a transition element, is 30. And that would be 2 in the K shell, then 8 in the L shell, 2 in the K shell, 8 in the L shell, 18 in the M shell, because it's in period 4. 1, 2, 3, 4. So hydrogen, sodium, potassium, calcium, yeah. And then 2 plus 8, 10, 28, 2 in the N shell. So you take this here, Okay. So we are now going to take the oxidation number of zinc to be +2. +2. And then the nitrogen, we now say X. Oxygen, let me what is oxygen is -2. Okay, now we can calculate this. So this will be 2 plus, because this is like zinc and this is 1 times 2, 2. Plus, we have this 2 here, 2 times x. 2 times x, right? 2 times x plus 2 times 3 times -2 equal to 0. Right? So we now have 2 plus 2x, 2 times 3 is 6. 6 times -2 is -12, equal to 0. So 2 minus 12 is -10. 2x minus 10 is 0. 2x is 10. So X is plus 5. So this will be zinc trioxonitrate 5. Zinc nitrate. Zinc trioxo, because of 3 oxygen. Okay, zinc trioxonitrate 5. That's it. This 5 is because of this plus 5. Right? Okay. We are done with these rules. We are done with the rules. Before we go into solving problems, I know this video is getting long, right? But let's at least solve a lot of problems in this video, so that the next video we can balance redox reactions. We can just work on balancing redox reactions. Now, before we begin to solve questions, I have so many questions here. A common question they ask is it possible for oxidation number to be fractions? You know, like I said earlier in the video, I said the oxidation number are integers. It could be positive integers or 0 or negative integers. I didn't talk about fractions. Okay, so technically, oxidation number of an atom, you know, it's not a fraction. No, oxidation number is an integer. Okay, but let us look at this. Let us look at this problem. I would like you to find the oxidation number of iron in the common name. The common name for this is tri-ion. The tri-ion tetraoxide. Tri-ion tetraoxide. Tri-ion tetraoxide. That's the common name. However, I want us to find the oxidation number of iron in that compound and give the IUPAC name. Okay? So, tri-ion because of 3 iron atoms, and then tetra 4 oxygen atoms. Now, I'm going to split this up. Let the oxidation number of iron be X. So I'm going to put X here. For oxygen, here is going to be -2. It is not a peroxide. It is not bonded with fluorine. So, and of course, the oxidation number of the entire compound is 0. So this will be 3 times X plus 4 times -2 equal to 0. So 3x minus 8 is 0. So 3x is 8. So x is 8/3. I now say, wow, what's the problem? Plus, let me put plus here because this is plus. So x is plus 8/3. I say, why? Oxidation number is an integer, not a fraction. As you see there, right? So why did I get this? Why? Does it mean this compound does not exist? It exists, trust me. So, you know, one thing with chemistry is, chemistry has a lot of rules and deviations. And guess what? It's still coming. I mean, God made this world like, I cannot even imagine how God created this world, honestly. Like, it's like there are discoveries all the time. All the time. Honestly. And we have not even discovered everything, no. I'm serious. So to tell you the magnificence of God, honestly, magnificence of God. So, in this case, let's do some explanations here. We have 3 iron atoms in this compound. Atoms of the same element in a compound usually have the same oxidation state, oxidation number. Okay, like I said, oxidation number means oxidation state. So atoms of the same element in a compound usually have the same oxidation number. However, it is possible for atoms of the same element in a compound to have different oxidation numbers. Let's look at what let's see what I mean here. We did a calcium phosphate, right? We did calcium phosphate. We did calcium tetraoxophosphate 5. Right? 2 times 3 plus 2 times 6 plus 2 times 4 times minus 2, 0. 3 times 2, 3 times 2 plus 2 plus 2 times x plus 2 times 4 times minus 2, right? 6 plus 2x. We did this earlier on, right? 2 times 4, 8 times minus 2 is minus 16, 0. So 2x minus 10 is 0. 2x is 10, x is plus 5. So this, but calcium is plus 2. Calcium is plus 2. Right? This means one atom, you have 3 calcium atoms. You have 3 calcium atoms there. Of course, this plus 5 is for phosphorus. And of course, this is minus 2. But let's talk about calcium. You have 3 calcium atoms. This plus 2 actually is 1 calcium atom. 1 calcium atom is plus 2. Plus 2. So 3 calcium atoms will be 3 times plus 2. 3 times 2, which is plus 6. So here, look at this here, folks. 3 calcium atoms is 6. But the calcium atom, 1 calcium atom is 2. What we've been doing all along is we've been finding the oxidation number of 1 atom. That is what we've been finding. Everything we've been talking about in this video, finding the oxidation number of this, it means of just 1 atom. If we want to find the oxidation number of 3 calcium atoms, then it is plus 6, not plus 2. The 1 atom is plus 2, but the 3 calcium atoms you have here is plus 6. Now let's get back to this here. This 8/3 means the 3 iron atoms. The 8/3 the 8/3 is 3 iron atoms. That is plus 8/3. 3 iron atoms. However, look at what happened. In this case, in this particular case here, each calcium atom is +2. So the atoms of the same element, atoms of the same calcium element have the same oxidation number here. Because here, each calcium atom is +2. First calcium atom +2. Second calcium atom +2. Third calcium atom +2. Here. But here, what actually happens is this. What actually happened is we have one iron 2 having an oxidation number of +2, and we have one iron 3 having an oxidation number of +3, and another iron 3 having an oxidation number of +3. This is actually what happened here. Now here, it's not like that. Here, one calcium atom +2, another calcium atom +2, another calcium atom, the third one, +2. That is 6. Okay? However, in this case, whereby you now have a fraction, in this case you have the same atoms of the same element, calcium is the element, atoms of the same element have the same oxidation number. However, here you have atoms of the same element, iron, but having different oxidation numbers. That is what you have here. So this is just, you can see this as an average. So oxidation number we have been calculating are actually averages. It is just for one atom. And usually atoms of the same element have the same oxidation number. Okay, in a compound. Atoms of the same element usually have the same oxidation number. However, it is also possible, as you can see here, for atoms of the same element in a compound to have different oxidation states, oxidation numbers, as you can see here. And when you have this kind of case, we call it fragmenting. It's known as fragmenting. So you see atoms of the same element in a compound having different oxidation numbers. Now, I know the question you're about to ask me. However, please, let's continue. Let's do some examples, and we'll probably have part 2. We're going to have part 2. But at least let's solve some examples, and then we can call it a day. And then we'll have part 2 to solve more problems before we now go to balancing redox reaction, because this video is getting long. I know the question you're going to ask me. I know. Trust me, I know. However, it's going to be in advanced chemistry. Okay? For the folks I'm doing this video right now, just understand that oxidation numbers, in essence, technically they are integers, period. Okay, they are integers. Technically they are integers, the oxidation states. Because The number of remember we said earlier on that the oxidation numbers is the number of electrons an atom gains or loses in combination with elements, with other elements or compounds. The oxidation number of an element is the number of electrons the element gains or loses when combined with another element or compound. So the number of electrons is a number, is an integer. How many electrons is an integer? So technically, yes, it's integers. Okay, but is it possible for some professors, when they are asked to calculate this here, and you give this is just like telling you that, okay, of the 3 ion atoms, the whole 3 ion atoms, they have a total oxidation state of +A. That is what it's telling you. Fragmenting is beyond the scope of this topic I'm teaching here. We can talk about it in advanced chemistry. Okay, but now let's do some more, let's do some problems and then we can call it a day. And then we watch out for part 2 of oxidation numbers. This actually now will be part 1. Okay. Does this make sense? Does it make sense? So the first questions I have here is, first of all, we'll start with simple ones. Calculate the oxidation number of the element in the compound, then give the IUPAC name of that element. Okay? Give the IUPAC name of that compound. All right. Question 1. Let's look at questions. The first one. The first one is nitrogen in N2O. N2O. So the nitrogen here, let it be X, and of course O is -2. This is not, this is N2O. So let it be X, and then O is -2. This is not a peroxide, okay, and it is not bonded with fluorine, so O is -2. So here we have that 2 times X -2 is equal to 0. So 2X, let me kind of split this here. So 2 times X -2 is 0, because this is 1 times -2. So 2X is equal to 2, so X is +1. So this, you can call this dinitrogen 1-oxide. Dinitrogen 1-oxide. Dinitrogen 1-oxide. Okay? Some people will say nitrogen 1-oxide. And this is known as, this is, oh, wow. So, guess what? When people are, when they are mean, you know, like some people, they are really mean, they don't even smile, that you might even see wrinkle is now part of their face. Have you seen some people? I mean, these are not old people, oh, these are young people, but because they're now so mean, or the way they express their face. You see, wrinkles are now part of their face. I'm not trying to, I didn't call anybody's name, okay? I did not. I didn't call any race at all, no. But some people are like that. You gotta be smart. You gotta smile. So, if you see anybody that is mean, guess what? If you see anybody with a mean face, put the gas, this is the gas. Let the person inhale this gas. Guess what? If the person inhales this gas, the person will be laughing. This is called laughing gas. Laughing gas. Laughing gas. Is a uncontrollable amount of laughter when somebody inhales it. Please don't try it though. I didn't say you should do it, no. So don't do it. Please don't do it. But this is called laughing gas though. When somebody inhales it, the person begins to laugh. Yeah. And it's used in initially it's being used as an before they do surgery. They give that, but that was olden times, not now. But it's called laughing gas. Because if you inhale it, you laugh. Okay, the next one is nitrogen in NO. No! No! In uppercase letter. No! Okay, let this nitrogen here be X and this is -2. So this is X minus 2 is 0, X is equal to 2. This is nitrogen 2 oxide. Nitrogen 2 oxide. Nitrogen 2 oxide. See that? Plus 2. Plus 2, please. Plus 2. Number 3, nitrogen in NO2. NO2, no 2. Okay, so let the oxidation number of nitrogen here be X, and then oxygen, of course, here is -2. Okay? NO2. Now this is a gas. This is not a peroxide, no. This is not a peroxide. Please, this is not a peroxide, no. Peroxides are like something like H2O2, hydrogen peroxide, K2O2, potassium peroxide. Okay? This is a gas, nitrogen 4 oxide, just like your carbon 4 oxide. But how do I know it's 4 anyway? Okay, so this is X plus 2 times -2 equal to 0. So X minus 4 is 0, and X is plus 4. X is plus 4. So this is your nitrogen 4 oxide. Nitrogen 4 oxide. Okay? 1, 2, 3, 4. Okay, let's do this one and then we can call it a day. These are oxides of nitrogen. Number 4, N in N2O5. N2O5. Okay? So let the oxidation number of nitrogen be X, and of course O is -2. So this will be 2 times X plus 5 times -2 equal to 0. So this is 2x minus 10 equal to 0. 2x is 10, so x is plus 5. And you can call this dinitrogen 5 oxide. Dinitrogen 5 oxide. Or you can call it nitrogen 5 oxide. Okay, you can also call this nitrogen 1 oxide. Nitrogen 1. Because when they say nitrogen 1 oxide, okay, you already know it is nitrogen and oxygen. So nitrogen 1 means that this is 1. And of course, oxygen is 2. So this goes here, and this is N2O. Right away. If you want to call it nitrogen 1 oxide, dinitrogen 1 oxide, it's the same thing. We are really not. The main thing for IUPAC is to make sure you put 1. Yeah. It's nitrogen 1 oxide or dinitrogen 1 oxide. Here, nitrogen 5 oxide or dinitrogen 5 oxide. We are not very strict in that you put di here or there. Because here, once you put nitrogen 5 oxide, if you just say nitrogen 5 oxide, okay, so we already know that it is nitrogen and oxygen. Okay, we already know it's nitrogen and oxygen anyway. So if you say nitrogen 5, that means this is 5. Oxygen we know is 6 or negative 2. Most cases it's negative 2 because it will easily accept 2 electrons to achieve the octet configuration. So this will be this here, and that is N2O5. Okay? Alright. So it doesn't matter whether you say dinitrogen 5 oxide or you just say nitrogen 5 oxide. It doesn't matter. It's the same thing. Alright. Thank you so much. We are going to stop here for today. Please watch out for part 2, oxidation numbers part 2, before we now do redox reactions. Thank you so much for listening to this video presentation. If you have any questions, please feel free to ask. And of course, this website has everything. Okay? Alright. Thank you. And you have a great day.